In example 4, we're going to be looking at a related rate problem that deals with conical tanks. And part of using cones is that when we're filling or draining water from a cone, all of these are going to be based on similar triangles. And so there's going to be a ratio between our radius and our height that's going to be true for the whole triangle, or for any cross-section of this, we're going to have a similar triangle. So in this problem, we have water running into the conical tank at this rate. Notice that's a change in volume, so we'll start by writing that as a change in volume with respect to time. It's going into the tank, so it's going to be a positive value. The height is 10 and the base radius is 5. Notice this is talking about the size of the tank, not the depth of the water. Now these are constants, but they're not going to be directly related to how much water we have in the tank. How they are going to be related is based on this similar triangle. As we fill this in, these angles are going to be the same and these triangles are going to be the same. And so I can set up a proportion connecting R and H. So for example, R over H would be equal to 5 over 10, or maybe better, R over H is 1/2. Now, I'm going to look at our volume before we decide what to do with that. So the next thing, we want to know how fast the water level is rising when the water is 6 feet deep. So deep would be, we're looking at when H is equal to 6. We want to know how fast the water level is rising. So since we're talking about the water level, we're talking about a change in height. So we're looking for dH dt. That's what we need to find. That's our goal. Since we're looking at volume and how it's connected to R and H, we're going to write out our formula for the volume of the cone. 1/3, the base is pi r squared times the height h. Now since we're looking for dH dt and we know what our height is at a certain time, what we want to do is we want to keep h in our equation. Now I could go ahead and substitute, take a derivative right now, but if I take that derivative, I'm going to have dr dt and dH dt. I don't have anything about r. In these cone problems, since we have the similar triangles, I can actually write r in terms of h. I know that r is equal to h over 2. I want to keep the h because that's what we're going to solve this for. So I'm going to substitute this in before I continue. This is going to give me h over 2 squared times h, and that would simplify to pi over 3 h cubed over 4, and that would actually be pi over 12 h cubed. So when I take my derivative here, looking for my rate of change in volume, dV dt, that would give me the 3 times the 12 will give me pi over 4 h squared, and since it's implicit differentiation, don't forget your dH dt. Now we want to substitute the values we have. Remember, we knew that our change in volume was 9, so we can substitute that in. Pi over 4. And we need to know our height. We are looking for dH dt, but before I can continue, we know our height right here. So our height is going to be 6. We go ahead and plug that in. So we're getting 9 is equal to pi over 4 times 36, which is going to simplify to basically dH over dt is equal to 1 over pi. To make this more useful to us, we could say that that's about 0.318. We need to give the correct units for this. Remember, we're talking about a change in height, and so that's going to be feet per minute. Now we should also probably interpret this correctly in terms of our unit, so we would change this to say the water is rising at 3.18 feet per minute.